Okay, welcome people to the pre-seminar on the World Quantum Day. I'm not sure if we're going to see some Planck constants, but anyway, so our speaker is Aaron Kettner, who is local here in Prague, and he's going to talk about group C-star algebras. Please.
Yes, thank you. Unfortunately, no Planck's constants or the word quantum today. It's about group C-star algebras. So they are quantum groups, yes. Okay, so we said the word, now we can countable. So gamma will be a countable discrete group. And we consider, so we want to construct, when I say group C-star algebra, I mean reduced group C-star algebra. So we want to construct the so-called reduced group C-star algebra of gamma. And this will be the C-star algebra generated by the image of the regular representation. Okay, so what's the regular representation? First of all, we take the Hilbert space L2 of gamma, which consists of all such sequences, which are, complex sequences with complex entries that are square summable. So the sum over all G and gamma of this AG absolute value squared, this is finite. Okay. So this, I guess, everybody is familiar with, or should I write down the inner product? I guess it's fine. Okay, so this is a Hilbert space, and we can define the so-called left regular representation of gamma on L2 of gamma just by shifting, right? So I call this lambda. This is a map from gamma into B of L2 of gamma. And what does it do? I take a basis vector in L2 of gamma, delta S. I'll define what this is in a second, and I'll just shift it. Let's say this is T, then this would be delta TS, where delta S, this is, so if I evaluate this, if I take like the Tth component, this is 1 if S equal T and 0 otherwise. Right, so I just, this is Hilbert space of sequences. This has a canonical orthonormal basis consisting of sequences that are equal to 1 in one specific entry labeled by some group element S and 0 everywhere else. And now I act on that Hilbert space with my group, or I represent my group on the Hilbert space just by shifting. Right, so the group element T gets sent to the operator that just shifts elements in that orthonormal basis accordingly. And so now we define C star reduced of gamma to be the C linear span of all such operators. And okay, we want it to be closed, so we take the closure, and we take the closure in the norm on B of L2 of gamma, right? Okay, so I take just the image of that representation basically, and you close it, and you can see that this is a C-star algebra. That's not so difficult to show. So this is the reduced group C-star algebra.
Unitaries.
Oh yeah, sorry. No, was I? Yes. So this is a unitary representation. So each of these lambda t or lambda s is a unitary operator, which you can see very easily. I mean, it maps, like you have this orthogonal basis, orthonormal basis, which are the deltas. And all we are doing is we're permuting these basis vectors, right? So that's definitely unitary. And yeah, then you can show that this is a C-star algebra, and this is called the reduced group C-star algebra. Okay, so this is the basic object that I think Tatwamasi is trying to understand. So if there are any questions just for this construction, then now would be a good time. Good. This guy. So that's this is the operator norm. So whenever you have a Hilbert space H, then B of H is the Banach space with this operator norm that's given by, okay, I take an operator, let's say capital T, and this is the supremum over all vectors that have norm 1 of T applied to V. That's the norm. Yeah, and then you take the closure in this norm. That's actually an excellent point because there is a norm on here that we use, but there is no unique norm on just this span, right? So we choose to take the closure in the norm topology, but we wouldn't have to. I mean, we could, for example, take the closure in the weak operator topology, and then we would get the phenomenon, group phenomenon algebra that I think Tatwamasi might also be talking about. Or you could take like an entirely different construction, and you could take like a completely different enveloping C-star algebra of this guy. And then you would get, for example, the full group C-star algebra. Like there's different versions of this, but we focus on the reduced one. And now the goal is to study the structure of this reduced group C-star algebra. And so, for example, what could you be interested in? You could be interested in ideals, or maybe the absence of ideals, so simplicity, or traces, or K-theory. And understanding these group C-star algebras is a very old part of operator algebras, and it's still a very active and big one. For example, the K-theory, that's basically the Baum-Conn stuff, right? Like computing the K-theory of this guy is what the Baum-Conn conjecture is supposed to do. So this is not at all easy. So we will talk about simplicity now, which also is not at all easy. And well, I guess, why do you study this thing in the first place? I think people think of this as encoding information of the group itself. So I guess the fundamental object you're interested in is the group, and then you study the group C-star algebra. Although those guys are also nice examples of C-star algebras. So I guess you can look at it from either point of view. Okay. However, that is so the point for this talk, and probably also Tatwamasi's, is that some properties of this reduced group C-star algebra can be understood by studying certain actions of G. Of gamma, sorry. Okay, so I want to say what I mean by this. So first of all, what's an action? So let's say X is a compact Hausdorff space. Then, which time do I have? Okay. An action, I think I gave a free seminar not too long ago where I also introduced actions, and I don't remember exactly in what context. So I'll do it again. An action of gamma on X is a continuous map. I guess in general you wouldn't have to ask it to be continuous, but we only want to look at continuous things. A continuous map from gamma times X to X. And I will typically write this as sending the tuple gx to alpha g of x. So we call the action alpha. So a continuous map like this, such that two things hold. First of all, alpha g composed with alpha h is equal to alpha gh for g and h. And the identity element of the group is the identity on X. Okay. And okay, so the way that, or one way to think about actions is as something dynamical, right? So you take points in the space and you move them around along group elements, or you move them around in the space using group elements. And in that spirit is the next definition. So an action is called minimal if for all x and x, the set of all points which I can reach from x by applying the action is dense in x. Right, so what this is saying is that if I have my space, and now I take my point x, and now I move around using the group action, then I see the entire space, basically. There's no area, like no maybe a small open set, which I don't reach. Like if I pick any open set or any open subset of my space, I will eventually land inside within the action. So that's somehow the idea. Like, yeah, you see the entire space, and that also means you cannot further restrict to some minimal subset, to some invariant subset, which is why this is called minimal. Like minimal in the sense of like irreducible. You can't further restrict it. Okay, so that's that. Secondly, so this is 1 maybe. This is 2. The point x and x is called a fixed point if alpha g of x is equal to x for all sorry, for all x. I'm not confused now.
Requirement of being minimal. It's not saying that it's transitive, right? It's requiring slightly less. Yes.
Right. So transitive means that there exists a point whose orbit is dense, right? But for one particular point, right? So minimality is stronger than transitivity in the sense that if you're minimal, then every point is transitive, right? Because every point sees the whole space, whereas transitivity just means there exists a point from which you can reach the entire space, but there might be other points where you can't. Yeah, yeah.
Each orbit.
Yeah, exactly. Okay, I think I slightly got confused in my notes, so I'll just change course. So alpha is called, we forget about fixed points, we don't need them. Alpha is called topologically free if the following set, no, sorry, I'm confused. I'm mixing something up. If the set of x in x such that alpha g of x is equal to x for some, okay, maybe like this, some g that's not the identity. Right, so all points where you can somehow return to that point using the action by a non-trivial group element. So this set should have empty interior. It's empty interior. Okay, I think that's correct. Okay, so that's topologically free. Basically, you don't want any fixed points. You don't want points where you can return to using the action. And okay, maybe for some topological applications to have no fixed points at all is too strong, but we ask that the fixed points have empty interior. Okay. Now, now we don't just have an action on the space itself. We can also define an action on the space of measures on the space. So if yeah, X is my space still, then M1X will be the set of all probability measures on X. So measures that have, like, if the whole space has measure 1, and then alpha induces a gamma action on this space of measures by saying that if I by use of notation, I also call this action alpha. So if I apply the action to some measure, I want to get a new measure, so I can say, okay, what should be the measure of some set y? This should be the original measure of alpha g inverse of y. So for it's measurable. Right, so I translate a measure by like shifting the space somehow. Yeah, I think the set of the measure of some set y in this new measure should be the measure of the set that I translate by the inverse of g. Okay. This is not at all divided in half, but okay. And then mu is called an invariant measure. If it's a fixed point of this action. Okay, I didn't define fixed points now. Say if yeah, it's invariant under this this action. So mu of alpha g inverse of y is equal to mu of y for all g and for all measurable subsets of x. Right, so if basically this means that my measure is such that the measure of a set y will not change under translating, right? Like I can move it around as much as I want, its measure will always stay the same. So an example would just be like the shift on the real line, right? Like if I shift a set, it's not going to change its, if I shift an interval, it's not going to change its. Okay. Okay, in this definition, not, but here I think you need it in order for this to be an action. Like if you apply like alpha g, alpha h, and then you have to flip it around, right? I think that's the. Yeah. Okay. Enough space. Now comes maybe a bit less intuitive definition. Alpha is called strongly proximal. if for all probability measures, the weak star closure of the orbit of mu contains a point measure. So for the weak star closure, I should say that we can embed this space of measures into the dual space of C of x. Right, so if C of x is a Banach space, I can look at its dual, and any measure defines a linear functional, a continuous linear functional on C of x. And so I have the weak star topology on here, and I can restrict it to this. That's this Ries-Kakutani representation theorem. Yeah. Yeah, in fact, like functionals on C of x, all of them are induced by measures. And so that's what the weak star closure means, right? So like all of this is happening inside here. This has the weak star topology coming from the dual of C of x. And in that weak star topology, I take the closure of this, which is the orbit of mu. So like I take mu and then I move it around using the action. And then I want to be able to approximate the point measure in this weak star topology. So that's what strongly proximal means. And now we will eventually circle back. So if you remember, I started with group C-star algebra. So what does all of this have to do with group C-star algebra? So my claim was that studying certain actions of the group helps us understand the group C-star algebra. And I'm getting to like maybe the most important result in this direction. So because one class of actions that are particularly important for this kind of stuff are boundary actions. So X is called a gamma boundary. If the action, so X is still the same compact Hausdorff space as before. So the compact Hausdorff space that admits a gamma action is called a gamma boundary if the action alpha is both minimal, which is defined over there, as well as strongly proximal. That's what a boundary is. And I think there is, I'm far from being an expert in any of those. I think there is a reason why it's called a boundary. I think it has something to do with like the Cayley graph of gamma. Is that correct? Like you take the Cayley graph and then you sort of look at the boundary of that, and then the group acts on that boundary, and this is like where this comes from somehow. So there's a reason why it's called a boundary, even though it's not obvious from this. But now there's an important fact, namely that there exists a universal such boundary. So what do I mean by universal? There exists a boundary partial f gamma that is universal in the sense that if X is any other G boundary or gamma boundary, if X is any gamma boundary, then there exists a map phi from the universal boundary. Sorry, usually for me groups are G, so I keep getting confused that it's gamma, but I wanted to stick to Tadlomatsi's notation. Yeah, so there's a map from this partial f gamma to x that is continuous and it's surjective such that it's also equivariant. So that means that if I apply the action to a point x in here and then I map it, this is the same as applying the action to the 0.5x in here. So yeah, I'm just using the dot here. So writing alpha g of x as just g times x because I don't want to give names to the actions on both sides. Okay, but I guess that's clear. So it should be equivariant in the sense that it commutes with the actions for all g in gamma and x in this guy. And then this universal boundary is called the Fürstenberg boundary. I should maybe Fürstenberg. Okay. Is what? I don't know, sorry. I don't know that much about this.
The equity boundary is a factor. Yeah, because the percent boundary is never metrizable. Unless it's one more. Yes,
so they have some examples.
Yeah. In concrete example of the personal boundary. I mean, not of the personal boundary, but factors of it is. Because the personal boundary is universal also.
Okay, so we.
Thanks. Okay. And now why did I do all of that? So I want to circle back to the group C star algebra, and then that's the last thing of today. This is due to Kalanta, Meredith Kalanta, and Matthew Kennedy in 2014, which was quite a big deal because, as I said in the beginning, these group C star algebras, people have tried to understand them for a long time, and especially one thing people try to understand is their simplicity. And they rephrased simplicity of the group C star algebra, reduced group C star algebra, in terms of the action of gamma on its Fürstenberg boundary. So C star reduced of gamma is simple if and only if the action of gamma on the Fürstenberg boundary of gamma is topologically free. Yeah, I don't know if that result will appear explicitly in Tadwamasi's talk, but I think that what you talk about is very much inspired by this, I guess, or like the general methodology of trying to understand group C star algebras through actions on boundaries. Meredith was your PhD supervisor, right? Yeah. Okay. Okay. So yeah, I guess that's that. Thank you.
There's questions. Yeah.
So how should I be thinking of strong proximality? Maybe this is a question for Tadwamasi. I don't know.
Yeah.
It basically means that given any measure, and you can always find a point such that you can push that measure to that point in the group by the group elements. So I can give a concrete example.
Thanks. More questions?
All related to the unique trace property.
It's also related to the unique trace property for group C star algebras.
Tadwamasi is nodding. You talked about that in Potsdam.
Yes.
Yeah, I guess this pushing the measure to a point probably helps.
As Alan said, since simplicity is topological freeness, unique test property is just the action being faithful. It's the equivalent. Right.
And so maybe for this partial f gamma, so is there some more explicit way to think of this space, or just okay, there's this universal property, but it's like it's not just going to be constructed, for example, out of gamma itself, that it's, I don't know, like a
I don't know. I mean, there is some way of constructing.
Yeah,
it.
in many examples, yes. I'll give an explicit example.
because yeah, kind of since you don't have much, right? You have just this discrete group, so you would guess that maybe you want to kind of use the group structure, and yeah, but I don't know. It was just okay if there's an easy way to like see this boundary a bit more explicitly, but you say in some cases you can easily do that. In general, it might be more complicated. Okay, thanks. So I guess from the online audience, there are not so many people, but if you want to ask a question, go for it. And if it's not the case, then let's thank Aaron. Thank you. And now there's a short break, and then there's the main seminar.